In this video, we will be exploring the Spacecraft Mapping tool on Predictive Science's new MHDweb 2.0. This tutorial is part 6 of a 12-part series that is designed to guide users through this website's data visualization tools. If you've not done so already, it is recommended that you review part 1 of this series, which covers in greater detail this website's architecture, general visualization workflow, and the mass run database. So with that being said, to get started with spacecraft mapping plots, navigate to the MHDweb landing page. Once again, that is predsci.com/MHDweb2, and then click on the spacecraft mapping button here. For the purposes of this tutorial, I'm going to take a time of interest as one of the Parker encounters. So let's see, I'm going to select Parker encounter number 20. And fetch the Thermo 2 for Carrington rotation 2286. And before diving into this tutorial, I just want to quickly cover what's going on sort of behind the scenes for the spacecraft mapping plots. So the initial phase of the data fetching pipeline is similar to the time series tool. In other words, hourly ephemeris is queried for a selected spacecraft utilizing JPL's Horizons API between the selected mass run's start time and end time. And then for each hourly timestamp within this range, the spacecraft's instrument readings for plasma flow speed is fetched from Goddard's COHOweb database. Where such data is not available, we use a default value of 400 kilometers per second. This flow speed is used to ballistically map particles back to the coronal boundary. If, in the case of Parker Solar Probe, the spacecraft position lies within the coronal boundary, no such ballistic mapping is performed. The resultant mapped positions are used as launch points for tracing field lines and determining if and where these particles map back to the photosphere. Spacecraft mapping is a fairly involved data visualization tool and has a lot of nuance to it, and as such there's a few things to consider when viewing these plots. Firstly, ballistic mapping results in a longitudinal shift of the particle position due to the sidereal rotation rate of the Sun, as well as a shift in time depending on the flow speed and spacecraft position. So ephemeris that lies towards the end of the selected mass run's time range will ballistically map to a time outside of the run itself. So, for example, on this Omni spacecraft mapping plot that we're viewing now, ephemeris towards the end of this time span, namely towards July 26, will map outside of the run that we're currently viewing. Even supposing that the plasma flow speed for these positions is 400 kilometers a second or 500 kilometers a second, it will still take a few days to map back to the coronal boundary, which will be outside of this time range. By default, we begin ballistically mapping from the spacecraft trajectory 7 days before the start of the run to allow a sort of buffer for this ballistic mapping. And you can see the points that are plotted here represent the ballistically mapped positions at the coronal boundary. Another consideration to keep in mind is what spacecraft is being inspected. Certain deep space missions have ephemeris that lie well outside of the run's heliospheric domain, so one can theoretically ballistically map from these positions to the coronal boundary, but it might not really make practical sense. So, for example, with Carrington rotation 2286, we could use spacecraft Voyager 1, and by inspecting the plot using this query time button down here, and I'll get into more about what is going on with the observation widget later, we'll see that at June 22nd, Voyager 1 was at 35,227.3 solar radii. Using an estimated flow speed of 400 kilometers per second, it takes about 2 years for that particle to map back to the coronal boundary. And so this exercise is really just to demonstrate that you have to be mindful when you're considering the spacecraft for this particular mapping. So I'm going to go back to Omni, remove the time queried, and we'll move on. So as you can see on this observation widget, we provide 2 sets of available spacecraft, namely those with readily accessible plasma flow speed data and those without. As you can see on the drop down to the right, we also include some planetary ephemeris that can be used as a sort of faux spacecraft mapping, for example, using Venus or Mercury. For the selection, we simply supply a default flow speed of 400 kilometers per second. It's the same value that is used when plasma data is not available for spacecraft from the left drop-down menu. The next thing that I want to point out is that when exploring a time-dependent mass run, the particular state that intersects with the time of interest is the state that is used to trace the field lines through the coronal domain. So this can be viewed underneath the plot header here. In a computationally ideal world, the timestamp for each ballistically mapped position would correspond to a specific state within the time-dependent run, which would be used to trace the related field line. But as these plots are generated on the fly, this would take prohibitively long to do, along with other complications, namely how to faithfully animate this interaction between ballistically mapped positions and states within a time-dependent run. So because we're using a steady state run, there's only one state to select from. But for example, if I was to select a time-dependent run, let's use the Eclipse 2024 Live. This will take just a moment to load in that data. You'll see that the sequence or the state that is actually being used to trace these field lines is sequence 2200. And if I was to select a different time of interest within this time-dependent run, you'll see the state that is being used changed right below this plot header. But for our purposes, I'm going to use the steady state run that we were previously looking at, which was Carrington rotation, I believe it was 2286, and the Thermo 2 version of that. Even though the field line tracing is done with a single state for the visualizations, just to allow for a more responsive user experience, the ASCII data and ECSV file that users can download will actually perform the tracing using the correctly mapped and ordered states. So just keep that in mind. This process can take a couple minutes depending on the size of the time-dependent run. So now we're going to look at, in a little bit greater detail, the observation widget. So I'm going to collapse the tool menu and examine some of the options that are available to you in this widget down here. So currently we're viewing Omni spacecraft mapping, but for any spacecraft that has data availability within this time range, namely Carrington rotation 2286, we can pretty quickly view a spacecraft mapping for that. So I can look at stereo ahead or solar orbiter. And for the purposes of this demonstration, we'll continue looking at Parker Solar Probe during this Carrington rotation, which, as you can see, has that signature spiral during the Parker encounter event right here. One thing that I forgot to cover earlier is this sync state time with ballistic mappings option here. Now this is particularly useful when considering a time-dependent run. So just to illustrate this, I'm going to go back and select the Eclipse run, which takes just a moment to load. And from here, what this option is going to do is, by toggling this on, it's going to take the median value of the times for the ballistically mapped positions and use that state to map field lines for the current spacecraft mapping plot. So because the time of interest that I've selected is the midpoint of this time-dependent run, and because we're considering Parker, which is very close to the coronal boundary to begin with, those timestamps happen to align, namely that sequence number 2200. But suppose I wanted to examine Omni data, which is near-Earth heliospheric data. You'll see that the sequence that it maps back to is not necessarily going to be the midpoint of this time-dependent run. In fact, it's a little bit earlier because of the time that it takes for these particles to map back to 30 solar radii. So once again, I'm going to return back to our steady state run for Carrington rotation 2286. And I'm going to select Parker Solar Probe from the spacecraft dropdown here. And since we're considering a steady state run, I can toggle this off. The next fields to consider are these time range start and time range end. This is indicating the time range for spacecraft positions that will be used to ballistically map and then map field line traces to the photosphere. So right now it's using 7 days before the run start until 7 days after the run end. However, if I wanted to, let's say, trim off the first part of this time range, in here I could input, for example, 2024, and we'll do start at, say, July 4th. And you will see that those positions that were ballistically mapped here have now been trimmed off from this time range. And similarly, I can do this on the other end of the time range, and let's say we'll put in 2024, 720. Now you see it has drastically reduced the number of positions by trimming off everything after here. Now at the bottom of the observation widget, you have the ability to select a particular particle mapping at a given time, which can be done by clicking the Query Time button down here. So by pressing this button here, you will activate that feature. Now, actually, before I move on, I want to quickly change the mapping that we're seeing behind this plot. So currently we're looking at a radial slice of the radial component of the magnetic field. But what I'm going to do is actually examine a coronal hole map so we can see where these field lines trace back to in terms of coronal holes. By default, if no value is supplied in this time of interest field here, it's just going to use the time range start up here. Since I cleared that field, it's going to correspond to 7 days before the run start. But let's say I wanted to examine a time that is later in this run, so we'll go with July 20th. And you'll see the spacecraft position move here. As opposed to the full spacecraft mapping, this option allows you to also view the spacecraft position in the path of the ballistic mapping. The lower left part of the plot displays the spacecraft ephemeris, the ballistically mapped ephemeris, and where the particle maps to at the photosphere. And in the lower right part of the plot, you can find the real or approximated flow speed. And once again, if you're examining a time-dependent run and you want to ensure that the field line tracing is performed using the state that intersects with the ballistically mapped position, you can toggle on this switch here. And lastly, we provide the ability to sample positions around the target spacecraft position, which effectively gives a sort of error interval and performing the corresponding mappings for those positions. You can toggle on that feature by clicking this right here. So effectively what we're doing is taking a Gaussian distribution of n positions that lie within a sphere of some radius r. So as you can see here, the sphere radius is 0.1 solar radii, but the spacecraft position in question is at 123.4 solar radii. So this is out in the heliosphere, and as a result, that cloud of points sort of overlap one another on this plot. If, for example, I set my cloud radius to 10 solar radii, you'll see here that the ballistic mapping and field line traces show up as this cloud of lines and points surrounding the queried position. Alternatively, if I'm looking at a spacecraft position that lies within the coronal boundary, so let's say if we look at June 30th, which I believe is within the Parker encounter, the radial position is 11.7, and that cloud radius of 10 solar radii is now much too large, and you get this really dispersed group of points. But let's say I change the cloud radius to, instead of 10 solar radii, let's say closer to 1 solar radii, the density of that point cloud is a little bit more appropriate for the radial position of the spacecraft. Now, let's say that you want to get a sort of clearer picture of what is going on with this cloud of points. So I'm going to set that back to 720, and let's increase the cloud radius back to 10 solar radii. And I'm going to set the resolution to be a little bit higher, and then open this plot in another tab, and you can get a really high definition view of how that cloud of points maps back to the photosphere. Also, the relative distance between these positions and the queried spacecraft position is mapped to opacity, so with less opaque mappings being further away and more opaque mappings being closer to the original spacecraft position. All right, so I'm going to go ahead and return to our spacecraft mapping tool here. And you'll see that we have these 3 widgets on the left side of the tool page. These widgets are inherited from the coronal hole map tool and the plot2D tool. So if you'd like a more detailed exploration of the use of these widgets, please refer to part 3 and 4 of this tutorial series. Lastly, and just to reiterate part of the time series tutorial, all the tools on MHDweb 2.0 allow users to download both the plot image that you are viewing as well as the underlying data that is used to generate the plot. So for spacecraft mapping, you have the option to download either a fixed width delimited ASCII file or an ECSV file. The ECSV stands for Enhanced Character Separated Values. It's a file format that was created by the developers of Astropy as a human readable file format that can be read into a Python script and produce an Astropy table. So it's similar to a CSV but provides additional metadata about the data contained in the file, and when read using Astropy will yield a table with native Python data types and relevant units, coordinate systems, and timescales. I have linked the Astropy package documentation in the video description below. For downloading the ASCII file, you can click this button right here, and for downloading the ECSV file, it's the button right next to it there. And that concludes this overview of the spacecraft mapping tool on Predictive Science's MHDweb 2.0. The next video in this series will go on to explore the white light tool. If you have any questions, comments, or concerns, please leave a comment below, and thanks for watching.